Learning cortical representations through perturbed and adversarial dreaming. This is a paper by Nicolas Desparois from 2022, published in the journal eLife. My name is Max, and with Peter, we're going to discuss this paper today. The research question is, how can a cortical architecture inspired by GANs be used to study learning cortical representations through perturbed and adversarial dreaming? So, to get the background to the study and stuff we need to know beforehand is that humans and animals, they're able to extract general concepts without extensive teaching, especially overnight. So you do something, you go to sleep, and the next day you know the task better. And what we also talked about in this course, there was in my paper that memory strengthening occurs through replaying individual memories during non-REM sleep. And in REM sleep, creative imagery is done by combining old and new memories. And GANs, which are generative adversarial neural networks, are really good at representing the cortical semantic representations, which is why the researchers used them. So this is the GANs want to represent the brain that actively tries to rearrange novel experiences and stores them in a meaningful manner. And now to Peter.
Yeah, as Max already told you, the authors got inspired by GANs. And actually, they also made use of autoencoders and mixed those concepts together and built their model by it. But before showing you the model, which might look a bit complicated, I will give a short introduction to GANs and autoencoders. So on this slide, you can see a GAN at the top. That's a very basic architecture, and again, it consists of a generator and a discriminator. The generator's purpose is to fool the discriminator into believing that its generated images are real images. But at the same time, the discriminator tries to distinguish artificial images, or also called generated images, from real images. And this is like an adversarial game, so there happens adversarial learning. And the whole purpose of this is that with this architecture, both parts get better and better while training each other. So the discriminator gets better and better at distinguishing real images from artificial images, but at the same time, the generator gets also better at generating artificial images that look more like real images. So it's a super smart architecture that really works well in deep learning. At the bottom part, we can see an autoencoder. An autoencoder consists of an encoder and a decoder. The encoder takes an original image, like this cute little cat, and tries to compress this image into a latent vector. This latent vector can usually store way less information than the original image can. So you can imagine, like you would remember an image, you would remember stuff like, okay, in this image is a cat, it's a cute cat, has a white background, and so on. But we don't know for sure for the most neural networks, autoencoder neural networks, what exactly they store in the latent vector. But usually it works kind of well. Now the decoder takes this latent vector with this compressed information and tries to reconstruct it into the original image. So those should match as closely as possible. Okay, now we have those two concepts, and we mix those together by taking the encoder part of the autoencoder and putting it into the GAN. And we can see it on the next slide. It might confuse you at first, but stay with me. It's basically only an encoder added and the storage, the purple rectangle. Only those two things got added to this. Maybe there's some rearrangement. But now, before the real image and the artificial image gets to the discriminator fed into, beforehand, we fed it into the encoder. And this encoder encodes it into a latent vector. And now this latent vector gets into the discriminator. And now the discriminator has to decide up on this latent vector if it's a real image or a fake one. But also we store this latent vector in the storage to later retrieve the latent vectors to the generator. And those vectors are the inputs for the generator. Beforehand, the generator would just get some random noise and generate some random artificial image. Now it gets those latent vectors of real images. Okay, this might be a bit confusing, but we will see in the real model how this actually works in real life. As datasets, the authors used CIFAR-10, which is just a dataset of 10 classes like airplane, cat, and birds, and so on. And Street View house numbers, which is just what the name says, house numbers, photos of house numbers. Okay, now we can see the model on the next slide. On the right, you might be also very confused, but stay with me. It's really the same thing as we just already saw. When we look at the most left part, we can see there's an encoder, which just takes the original image of this little cute dog and creates a latent vector. Then we can see a red D, which is just a discriminator, which takes a look at this latent vector and tells us, is this a real image? And now here it's named an external stimuli because it comes from the external world, or is it a fake image, or it's also called an internal stimuli because it's from us internal, from the brain itself generated. Okay, now this goes into two other components. First of all, this latent vector goes also into the hippocampus and gets stored in there. And the third component this latent vector gets into is the generator. And the generator just tries to generate an image from this latent vector. Okay, we can also see 3 different phases here. You can see them on top of this image. Those are storage, replay, and creative replay. And those 3 phases are also called the wake phase, the NREM phase, and the REM phase. Those might sound familiar to you. I will explain each one separately, so it's easier for you. The first phase, the wake phase. It's just there for encoding and storing sensory information. So we have this little dog, and this whole process is basically the autoencoder, which I already showed you. So there's this little cute dog that's encoded into a latent vector. The discriminator tells us, should tell us, that's an external stimuli, it's a real image. Then this latent vector gets stored into hippocampus, but gets also into the generator. The generator takes this latent vector and tries to reconstruct it as closely as possible to the original image. And at the end, the error gets calculated by the closeness of these 2 images, and they should match each other as close as possible. Okay, and the next phase is perturbed dreaming, and that's the first concept they try to integrate into their model. This happens during NREM sleep, and here the discriminator gets just deactivated for this phase, so just ignore the discriminator. Because here the generator starts by taking a memory out of the hippocampus, also called replaying a memory out of the hippocampus, and tries to reconstruct this image again, but now it applies some occlusions to the image. So we have a reconstructed, occluded image that we feed into the encoder. The encoder tries to again encode this reconstructed, occluded image into a latent vector, and now the replayed latent vector and the encoded, reconstructed of the occluded image vector gets compared, and they also should match as closely as possible. This is the training goal of this phase. The purpose of this whole phase is to enhance the robustness of latent representations. And as we can later see, this actually works really good. The third and last phase is adversarial dreaming. And that's the last concept there. And we already heard as adversarial in our GAN introduction, where it was adversarial learning. So please remind yourself of that. And the purpose of this is to extract semantic concepts. What is meant by semantic concepts? It's like when you learn different concepts of math in school and your brain combines those, so you have an integrated understanding of different concepts of math. So what happens here? Here again, the generator takes something from the hippocampus, but not only one memory, but two. And to this, it adds noise to be a little bit more spicy. And now it has this combination, this mixture of things. And again, it tries to reconstruct an image. But now it cannot be the dog because it's a mixture. And now you can see it's a weird car that looks a bit like a dog, but not really like a car. Again, this is fed into the encoder. The encoder tries to encode it again into a latent vector. But now it shows it to the discriminator. And the discriminator is supposed to tell that's a fake image, that's internally generated. But maybe it fails to do it. And yeah, that's the adversarial dreaming. The discriminator tries to get better at distinguishing if it's a real image or a fake image. And the encoder tries to help the discriminator doing it. But the generator, at the same time, tries to fool the discriminator. And yeah, also this is really working well for extracting semantic concepts, as we can see later. So to show you the first finding, the authors trained the model on sensory inputs, as you can see on the left in the wake phase, and those are just usual images. And the early training phase, we can see, okay, the generated images don't look real at all. But after 50 epochs, we can see, okay, if we train the model, it actually works. At least we can see generated images that look somewhat real. And we can also see this when we look at the Fauché inception distance. Sorry for the wrong pronunciation. We can clearly see in the early training the Fauché inception distance, which just basically means how realistic an image looks. So less is better in this way. Less means it looks more realistic, and we can see in the early training it looks less realistic, and late training both data sets show, okay, the images that were generated are more realistic. And further findings will now be presented by Max again.
Yeah, great. Thank you very much. Yeah, as we have seen, that non-REM is there to robust the latent representations, the memories. So what they did with the model, they excluded the non-REM phase. And you can see that here they took the occluded photos, the occluded pictures from 0% occlusion to 100%, and they compared the two models, one without REM, non-REM, and one with. And you can see how much worse the model without non-REM is at linear separability. And this is for both data sets. What happens if we exclude REM sleep? So here they got a third graph, as you can see at the bottom. There's also the without memory mix. So in the REM phase, we have two images that are combined in the model, but without the memory mix, we only have one single image as an output and as an input. So you can see that here, even though we only have one single image, it's still better than not having REM sleep at all. And as we can see from last slide and here with the linear separability, both REM and non-REM sleep are so significant to the performance of the model. As we can see, the PAD contributes to an increasing separability of the object classes. Here we can see the PCAs of the three models, so one without REM, one without non-REM, and the PAD is so much more separable as the other two. You can see it here. And what we see in the intra and inter-class ratio in figure E is the lower the bars are, the better the model works and the lower the ratio is. So excluding REM or non-REM is basically the same as no training at all. And in figure F, we can see this is the ratio of clean and occluded, so not occluded and occluded pictures. And here you can see how significant non-REM sleep is for this phase, as REM sleep is actually lower than full model. So is it better? No, the REM phase is there to confuse the encoder, and this is why here because the confusion does not happen, it is actually performs better on distinguishing between clean and occluded. So both phases are significant for learning and consolidation of cortical representations. So this is not really a novel finding from this paper, but what the researchers wanted to do is find a model which is also easy to implement. So they got implications from this which are even further than usual papers, I would say. So for example, they imply a negative correlation between REM sleep quality and hallucinations, since impaired REM sleep also means an impaired discriminator. And this means there's no way to distinguish between real and fake. Therefore, you might have hallucinations during the day. Also, insufficient REM sleep also leads to poor performance on creative tasks. And they also imply that impaired REM sleep leads to slower learning speed. And that in this model, there must be non-REM dreams. As we have seen, the perturbed dreaming is still occurring, which means there could be dreaming in non-REM phases as well. So, what we find in this paper are a huge point of discussions. So they discuss their own model as well. And they also discuss that their model is definitely oversimplified and it does not represent true hippocampal functioning, and they also did not include oscillations at all, which, there might be other models which are better at doing this. But they actually wanted to do it so it's easy to implement for further research and for other studies. And they only did this in the REM phase, the mixing with two memories, which does not really represent the complexity of the human brain. They also did it only on image data and not other concepts and text or something else. In the order of sleep phases, they are not considered in this model, so they only did wake, then non-REM, and then REM phase. And they did not include other phases or any other construction, and if they would switch them, it didn't matter. Also, they used confusing terms in neuroscience and machine learning, and sometimes they did not even explain where they got this term from, and that was a little bit confusing in this paper. And also, they're neuroscientists and not machine learning researchers. That is why sometimes they used neuroscience terms for actually machine learning terms and vice versa. But overall, you can say that this paper has its limitations on a purpose, but it can be easily implemented to other research areas. And also it models the sleep and the computational benefits of sleep very well here, and you can display it very easily. Yeah, that's it. And yeah, I hope we will have a cool discussion about this paper. And well, yeah, thank you very much for listening.